Okay, so finally I would like to discuss one more state-of-the-art algorithm for continuous control. This is known as DDPG, Deep Deterministic Policy Gradient. The performance of DDPG is usually not as good as soft actor critique. However, it's much simpler to understand. I'll explain it to you very quickly. The idea is very simple, and also the implementation. It's fairly easy to implement that. By the way, it is one of your home assignments. So you will implement this algorithm, and luckily it's easier to implement compared to soft actor critique. So let's quickly go over this. So we would like to generalize, so DDPG generalizes DQN, Q-learning, deep Q-learning, to continuous actions. So let's look at the original DQN algorithm. If we're considering discrete action spaces, right, if you remember, we defined a Q network that gets as input the state and it outputs a Q value for each one of our actions. So a vector of Q values, one value per action, and then we can easily define our policy as the action which maximizes the Q value over our output. Right, and we've seen before that we train these Q networks using squared temporal difference loss, right, where our target value is simply the one-step look ahead, one-step TD value, the immediate reward plus discount factor times the max Q value of the next state that we arrived at, and then we define the squared error loss, and we can easily update the Q network. You already did that when you implemented the DQN algorithm. But now let's consider continuous actions. So the question is, how can we define a Q network for continuous actions?
You would have to output a distribution for each action, a probability distribution.
A probability distribution for each action? No, so now I would like to compute Q values.
Q values, okay. Not a policy.
No, Q values, Q network.
So you would have to give action as an input?
The action as an input, right, and then the output would be a Q value and it can take any action as value. Right, so we'll define a Q network for continuous action as follows. We simply set the action as an input, and now I can give any action as an input, even a continuous value. But this raises two questions. Number one, how do we get the max Q value in the next state in order to get a target value to train our Q network? And number two, how can we get the policy from this, right? How can we ask what is the action that maximizes the Q value? Right, so now it becomes non-trivial in this case. So DDPG, Deep Deterministic Policy Gradient, allows us to, provides us with a solution. It does so by training separately another function approximator, a policy approximator, an actor. We'll define it with pi of s, but this is a deterministic actor, unlike as opposed to soft actor critique. Right? Given a state, it will output a specific action. Specifically, we would like it to output the action that maximizes the Q value according to our Q network here. Okay, so we'll train the approximator to output that, although it's hard for us to know what that is. But once we have that actor, right, say for instance that we were able to train it, now we can solve this issue number one, right? Because instead of taking the max over all of the Q values, we'll simply take the Q value for the action provided to us by our policy, right? Provided for us by the policy that hopefully provides us with the argmax action. But how can we train this policy that provides us with the best action according to the Q values? So this is what's done in deep deterministic policy. The idea is pretty simple. The Q network is updated as we just defined, right? By updating all of the values inside the Q network using the square TD loss, where Y, the target value, is defined using our policy, right? Because we cannot iterate over all of the actions. How do we train deep policy? So this is interesting. We backpropagate the gradient not of the square TD loss, but of the Q value itself, the Q value as is, right? What happens if we compute the gradient of the Q values with respect to all the tunable parameters? It will tell us how to change the tunable parameter such that the Q value will increase. I don't want to do that, right? I wanna train my Q value to be exactly, well, my target Q value. But I'm going to continue to propagate the Q gradient all the way back through my network using backpropagation, all the way to the input, to the action input specifically. What will that tell me? It will tell me how to change my action such that the Q value is increased. I'm interested in doing that. Okay, this is something I'm really interested in doing it. So I'll take this gradient, the change in action, the change that I should have in action in order to increase my Q value, and I'll take this gradient and push it into my policy network. So now I'm tuning my policy network such that it will output an action that improves the Q values. If I do it sufficient amount of time, this is just stochastic gradient descent, I'm hoping to finally converge to the best action, the action that maximizes the Q value, such that the gradient will be zero. It will tell me you cannot change your action to improve the Q value, so at the best Q value. Okay, so this is exactly the idea behind DDPG. We won't go into the pseudocode, but that's in general exactly what it does. Okay, so we have a loss function for the Q network, a loss function for the policy, which is exactly, as you can see, a gradient of the Q values. So the pseudocode is exactly what I just tell you in the basic version. And you can see the target policies and the target Q network is updated using the exponential moving average, okay, like we saw in soft actor critique. And as I said, this is common practice these days, also in DQN. Although the original DQN did it every so often, this is common practice these days, to do it as an exponential average. One more important thing, we don't want to follow a deterministic policy, because then we don't have sufficient exploration. So we inject exploration artificially in DDPG by, when we choose an action, we actually randomly pick some noise value, and then we sample a Gaussian where the mean is the output of the policy. That's the mean, but we take actions that are slightly, well, sampled from a Gaussian around this value. But we have to inject some noise. We do it pretty artificially here and not in a structured way like we saw in soft actor critique. Okay? And this might be a bit of one of the reasons that DDPG doesn't work as well as soft actor critique, because the exploration is not very informatively directed. Okay, finally let's see some results. Final comparison between soft actor critique and DDPG, but also we include here PPO, DDPG, soft actor critique, we saw that already. VPG we didn't discuss, don't worry about that. And TD3, I'll just say it's kind of similar to DDPG, it has some enhancements. We won't go into that. To solve some instabilities in DDPG, so think of it as DDPG with some extra tricks to enhance it. But conceptually, you can think of it as an enhanced DDPG. So as I said, in many cases, in most of these Mojuku domain, you can still see that soft actor critique is indeed performing very well, but you can see that TD3, and in some cases DDPG actually is better even than the TD3, is not far behind, right? Probably except this one. And as I said before, there are some advantages to DDPG, or TD3, over soft actor critique, which are simplicity, right? Some would say, oh, you know what, I just presented both algorithms with all of the derivation. Some would say that VDPG is simpler, also TD3 by the way, with the enhancements. It's simpler to understand and to implement. You'll be the judge of that. And in any case, you're going to implement that in your home assignments.